Hello, everyone. Thank you for attending this first seminar dedicated to big data management, presented by Professor Serge Miranda. So during the whole presentation, you will be able to ask your questions on the chat, and Professor Miranda will answer them at the end of the presentation. Professor, I give you the floor, and good presentation to all of you.
Okay, thank you, Mishket, for this introduction. So this seminar is the first one of a larger series, which is part of two master degree, MBDS at the University Côte d'Azur and BR Master at Estia School of Engineering. And it's a special seminar on big data and artificial intelligence, which encompass 5 conferences by colleagues from France, Spain, and Italy, and 2 startups presenting use case. That's the way we built it. And it's dedicated to beyond these 2 master's program to any student, any graduate student, like a Miage student in France, and of course industry people, since we are closely connected with industry and we are working both for research and education with them. And next week, that will be my colleague from Bilbao University, Alex Ryan, presenting big data applications. And you have the list. Watch out also, that's always 2 p.m. CT, but 1, beginning January, because my colleague and friend Alban is from Tahiti, and about 10 hours of jet lag and time difference. So therefore, he's waking up at 7 in the morning, starting at 7 a.m. in the morning, and that's 6 p.m. for us. Otherwise, it's always 2 p.m. So that's part of 2 master degree, and these degrees are online. The 2 first European master degree online have been built by our team, first EMBDS and EBR. And we also have, and I will not talk here, of course, but I will address at the end, the fact that we have 2 skills extract from the master degree, as a matter of fact 7, but 2 are starting in January on AI and big data for continuous education on the FUN MOOC platform. So this conference is called Data Axis MUNDI. I wanted to have an idea of a title, how data plays a key role between reality and virtuality. And here I got this idea of Axis MUNDI. Axis MUNDI exists in whatever religion, whatever methodology in the world, in order to make the connection between Earth and sky. I would say between reality, physical reality, and sky as a limit. And therefore, if you look at this, you see that data is building a bridge between real life and data analysis as no limit at all. The sky is the limit. So Axis MUNDI, it's world axis, it's cosmic axis. You have this all over the planet with different symbols, either natural or built by man. And before starting, I like to have you an answer to these 2 questions, because that's part of our personal life, professional life, and public life. First of all, what is a quantity of data to get a digital twin? Well, it's not the order. The answer is 1 terabyte. And we have the answer because there is a great project conducted by Dr. Jim Gray when he was at Microsoft, and he built on digital twin for Einstein, and you could ask questions today about concerning life of Einstein, but you can ask him present questions. What about the COVID? What about etc.? You can ask him and he will answer. So that's a beautiful artificial intelligence tool which has been built by Jim Gray, called Digital Immortality, 1 terabyte of data. And that's the ambition tomorrow, is to collect these terabytes of data and to make you capable of discussing with whoever in your grandson, etc. So that's the minimum. And then you see petabytes, exabytes, zettabyte, iota. That's numbers you will have to understand. For instance, the first question, what is the quantity of data produced since the beginning of humanity? 12,000 years. This figure has been given by Eric Schmidt in 2010 when he was a CEO of Google, and at Davos meeting, he said 5 exabytes of data. 5 exabytes of data have been produced. And 1 petabyte, I put 1 peta and 1 iota in yellow. 1 peta refers to the glass wall for traditional database systems. The most important database in the world is about 10 to 15 peta. And of course, you know, one of them, which is the CIA database, which is about 100 petabytes. And also Walmart data warehouse is in the same order of magnitude. So petabytes is more or less the limit we have today with structured database. And then we talking about exabyte, zettabyte, and tomorrow yottabytes. There is a project from the American Defense Agency called the Iota project, 10 to 24. Just to mean here, we would like to track not everybody on the planet, every plant of the planet, every animal, whatever. That represents 1 iota. So just think about this huge amount of data, which is around us and which could concern everybody. Of course, this has been amplified by the COVID. I just put here some information on that. Just look at Zoom. Today we're using Teams, but the same figure for Teams. Look at the growing of Zoom just last year since March. They multiplied by 30 the number of connected people. And same at university where we concern. Today I'm giving a webinar. I'm in my room, like any student in the planet today. I mean in France, and just I'm doing my lecture. I hope you are there and you are interested. That's it. And in order to get started and to present the contents of what I'm going to share with you, I just took 5 documents I received in the last 4 days. For instance, December the 2nd, I received an information about blended learning. Adios amphi, farewell to amphitheaters. That was a nice article in Le Monde. And they say that in '68, when there were the French academic revolution, they say stop the courses in amphitheaters where there is a magister, etc. Stop it. And nobody could achieve it but the virus. And then concerning artificial intelligence, a very important paper concerning I would say the discovery which could help in solving some key issues on cancer research, namely. And here that concerns the 3D representation of protein. 3D representation of protein, and they work on an issue. 50 years ago, people started. 50 years ago, doctors and scientists started working on that, and they didn't discover anything concrete. Now they did. That's a paper. I receive a URL here. And then from China, a village in China, they put QR code. We entered the location-based society. Every place has an address, every object, etc. Here, 130 trees in China represent a QR code. So if you go by plane, you can take the peak and get information on that city. And then I received that book, very interesting book. Of course, I didn't read it through it. I just went through it, and I say the data imperative, a book I received this weekend. And yesterday, another research report from SAS on innovation from data to business. How we talk about innovation as in conclusion. So the contents of my talk is very simple. share with you the concepts. Share with you the concepts. In any science, there are concepts. So my ambition here, my ambition here is to share with you the fundamental concepts of big data and artificial intelligence, which are opening the road to many innovation in the future. So any concept I will use from data to big data will be defined from deep learning, NFC, Li-Fi. If I have time, I'm going to pack on these conference slides. I will make available the complete set of slides, but I will pack. Today, I'm a hand. And I will infer from that and from our experience of 20 years of innovation with students on disruptive technologies. That's what we have been doing for more or less 30 years now at University of Nice. I will infer three dimensions. The bottom-up paradigm, little big data, and smart place. We enter an area where every place will become smart due to the fact that we holding somewhere in our pocket or in our bag a smartphone. And as a conclusion, I will try to share with you something coming from Harvard. A colleague from Harvard, Gary Pisano, gave its vision of data innovation, and we built some kinetics there regarding economy and business model. So that's part of something also I'm doing in a conclusion. Raw resource of this millennium, same concept than love and happiness, that's data. Happiness is a marvelous thing. The more you give, the more you are left with. Le bonheur est une chose merveilleuse. Plus tu en donnes, plus il t'en reste, like a data. This presentation is a PDF today. This PDF, you can have it. It will remain on my computer. It could be in yours. 1 minus 1 equal 2. That's nice property. It's not this raw resource of this millennium are this very nice property. You enrich when you share. That's usually not the case with the dollars or gas. And then you have other laws, and we can play on that. And sharing with my friend and colleague in Haiti, Franz Varela, I would like to say that poverty is data access denial, meaning you need to provide today access to everybody on the planet to provide them with data they may need in order to live, to make a living. And that's, for me, one thing I'm very positive and proactive anytime I can. I summarize here 20 years of innovation at MBDS Innovation Lab in Nice, at University of Nice. Looking just at the sponsors, hardware, software, we lived 4 Copernician digital revolutions. 30 years ago, the people from hardware were leading the world. But then they noticed they were turning around. Then that was software people running on any platform. And they say everybody, and they noticed they were turning around 10 years later. And then finally, in the middle of the world, there is the user. We call it userware, and we can distinguish here 2 dimensions, data and services. So that's the reason I talk about serviceware and dataware. And big data and data science are disruptive technology in order to collect data, analyze data, and to provide added value services. If we look at IBM, Oracle, etc., their vision of the future, that IBM talk about CAMS, cloud, data as a service, analytics as a service, mobility, meaning smartphone, social networks. If you look at Citigroup, one of the biggest bank in the world, the CEO talk about smart social mobile application and cloud. If I look at Oracle, just to have a small positive aspect of MBDS, but for them they're talking about CI MBDS, so the cloud, IoT, big data, mobile, and social. And this represents skills we have within our master programs. And these skills are built also on graduates available for continuous education. So and that has been amplified by the COVID, we living a strong paradigm switch with the data revolution. And it's not only the digital revolution, it's a digital data revolution. The world is changing. I say to the students listening today, always be audacious, be out of the box, think out of the box. You have a good reference here. Michel Serre, also with whom I am participating to an honorary seminar pretty soon. Michel Serre is a kind of philosopher capable of talking about science, and he has both aspects, and that's a wonderful philosopher and scientist at the same time. So he said that word, everything is law. Look at Moses. He looked at the 5 most prominent Jews in the history of humanity. Moses, everything is law. Then Jesus, everything is love. Then Karl Marx, everything is money. Then Freud, everything is sex. And Einstein, everything is relative. And finally, Jim Gray came around and he said, everything is data, and you will see that pretty soon. Data as prefix or suffix exists everywhere in computer science. I just put in blue those who are part of what the students learn when they are in the master degree, and the one I may use today, but you see new jobs around data, you see many prefix word and many suffix word. So we entered the data-centric economy, the data deluge, and also dataism. That's the title of another book. So the next big wave is data. So the key question is, what is data? Also, we're talking about big data, and then from a natural point of view and computer science point of view. So you see the graduation, data, information, knowledge, insight, wisdom, and conspiracy theory. Data stems from the fact that man has 2 major defaults. Man forgets and man can be wrong. Errare humanum est. Man forgets. And because he can forget, he has to physically write something somewhere in order to not to forget. So what is data? The simplest definition I may share with you is the recording of anything, fact, measure, video, drawing, etc., on any support using a given code. And the first writing for men comes from these mud tablets in Mesopotamia. And do not forget the first tablet, that's interesting, the first tablet which has been even written by man's hand concerns a database, a fiscal database, That's when the writing, there was a city, with the city there were tax. Who is paying his tax? So that was recorded. So the first writing from human being is a database, and it has been stolen when the American went into Baghdad, by the way, in the museum. So nobody knows where it is. But then you can write on a wall, you can write on Facebook, you can write in books, on a digital support, recording of anything on any support with a given code. And data is the plural form of a word in Latin, which is datum. Datum is the fact of giving. The fact of giving is a datum, and the plural form is data. So when talking about datum or data, you're giving something else something. You're giving something else something. So that's interesting. And then, I mean, if you're giving, somebody is receiving it. And the symmetric word in Latin is captum. And that's interesting to have selected the word capta in order to, instead of information, to talk about what you receive from what somebody else left somewhere. So datum, data, the fact of giving. That's the word dare. Dare means give in Latin. And then, so we define data, capta, information, and then knowledge. Knowledge, then I have to go to Aristoteles. Aristotle said knowledge is three things: episteme, techne, pronesis. Episteme is science, knowing. Techne, technology, is knowing to do, how to do. And pronesis is wisdom, knowing to be. And I would say in 5,000 years, man invented a lot of artifacts, a lot of things, but he made a huge discovery. But in terms of ethics, I would say recently there is kind of a consideration at the world level, but ethics is of prime importance, and it has been somewhere forgotten. So do not hesitate about this. So now we have the data. We can say, what is a smart object? Many people talk about smart city, talk about Internet of Things, IoT. What is a smart object? A smart object is just a couple, data plus communication. Any object in the future will produce data and will share it. And that's important to consider the fact that every object in the future will produce data. And if I look from a biological point of view, I would say that every object will become alive in the future. Life in biology is defined by a couple, data plus communication. That's another area I could comment in other consideration, in other meetings, in other webinars. So IoT, we go from IoT to Internet of Everything. Every object will become alive tomorrow and will have to be integrated this way. Objects will communicate much more than human beings. You see, the Gartner gives a figure that years about there are 8 times more communicating objects than human. And of course, IoT produces a lot of data. That's a catalyst for big data. So now we're ready to talk about what is big data. Big data, data and big, of course, it's huge. I will not comment these figures concerning big data just to mean everywhere we impact it. Just consider that algorithm will alter the job of 1 billion workers on the planet today. Or second, I put here more than 80% of internet transactions are processed today by machines. A huge amount of data, and not only for reading, for transactions, for writing. So that has been defined by Mike Stonebreaker, who got the Turing Award some years ago. And Mike Stonebreaker is one of the most important professors in the US, initially at Berkeley with Ingress, Postgres systems, and now at MIT with VaultDB. Is recognized as the most productive colleague in the US in terms of data store system, data management systems. Any type of data systems went into his hands and his students. So he gave a definition of big data, and let's keep it because there are very few systems today which match this definition. The 3 V, volume, variety, and velocity. 3 properties of the data, of the big data. First, volume. I already quote Eric Schmidt at Davos saying the man produced 5 exabytes of data in 5,000 years. But what is interesting is the fact that today in 2020, that's almost every second. Every second. There is an interesting Berkeley report, which is a live report concerning the data produced on the planet, and you can find it easily on internet. And so just imagine that every second this year, man produced as much as data as human beings in 5,000 years. So volume. Variety from a computer science point of view. From a computer science point of view, data encompasses 3 parts: structured data, semi-structured data, and structured data. Structured data means there is a predefined fixed schema. We apply a model to the real world and we get an abstraction of that real world called the schema. And here we have an interface of the past, present, and future, an Esperanto for data management, which is called SQL, Structured Query Language. And its variant like Object Query Language. So structured data represent today 90% of data managed on that planet. And since I have students also coming from economy attending it, just structured data is very simple. Look at the information your bank has concerning you, name, first name, family name, address, telephone, and account number, etc. That's an example of a structuration we have on data. So that's traditional data. And then we have the web data, referring by semi-structured data. Here we have a standard like RDF. We have interface which looks like SQL called Sparkle or Ontology Web Language. And here the characterization of this semi-structured data are the existence of tags, what we call metadata, data on data. And that stems from the XML standard we have on the web. And then everything else, which is unstructured data, a like on Facebook, on social network, a captor sending an information. And here is a word of no SQL, not only SQL, which means no relational, but which means SQL in the future. So that's weird. The three different types of data, variety of data, we integrate when talking about big data. So we may have different sources of data with different variety of data, and they have to be managed in a single space called a data lake in order to be analyzed by mathematicians or artificial intelligence people. Third, V is velocity. Data are flowing. And look at what happens every second on internet. You have internetlivestats.com in 1 second. You have you can look at it. I just looked recently what happens every second, well, I will not comment that. Just imagine 1 hour of video posted on YouTube every second. 1 hour of video posted on YouTube every second. 90, more or less than 90,000 videos seen on YouTube. And then you can, but watch out, one identity theft every second too. So big data is the evolution of computing boundaries. Look at volume, variety, velocity. Today, globally in 2020, we're talking about 40 zettabytes of data. Variety, you see the data coming from the web, coming from production database, coming from social network, from internet. That's variety. The three types of data we have from computer science, and then velocity. And you see in front the technology, the cloud, big data, and smartphone mobility. That's the framework we have to keep in mind when talking about managing and analyzing data, the big data of today and the future. Correlations is more important than causes. So sometimes we learn from data. That's called data learning, and you will see we talk about machine learning and deep learning. So here, that's a way, that's called datafication. I will not comment more than that. And if I type today definition of big data on internet, you will see 8V. Every person wants to put another V is welcome. So tomorrow it will be 9V, etc. But the 3V are the basis. There is one which is of prime importance, is value, the quality of data. So this force of value, you have to work, you always have to work and eliminate fakes and biases, etc. So the value is of prime importance. And then we talk about little big data. What in this large amount of data, what is of concern to me? What refers to my life, public, private, or professional? That's called, you have a free application like Mood Meter, you can see what is your mood today. Mine was pretty good today, even though I had this webinar. I didn't have any stress, so it was life was good for me today, and that's refer also to the quality of connections you have to the real world. My digital twin was happy today. And do not forget also that the data war tomorrow is on contents. You see that, you may have seen that for TV, you may have seen that for soccer, football games on TV, rugby games, sports, etc. The battle is on contents, and that's not only TV working there. You see many contenders who are on Facebook. Facebook got I think the rights of the football in Brazil, etc. So today the war is on contents. And do not forget this digital rule. When you do not pay for the product, that means you are the product. You're providing free information to social networks, and they could use it in order to build dynamic profiles and provide you for dedicated advertising. Cloud computing is the future. Everything will be as a service. Data as a service, analytics as a service. And that strategy of the big ones, Amazon, Oracle, Google, IBM, etc. If we look at parallelism and big data, we're talking about larger numbers, just a terabytes per second. A typical hard disk is 100 megabytes. How you could achieve a terabytes per second? But putting thousands of disks in parallel, 10,000 hard disks in parallel, then you got a terabyte per second. And then, in order to look at parallelism, you have two major approaches, scale up or scale out. Scale up, you're building servers more and more powerful, like the Teradata machine, which is managing the CIA database. That is managed by Teradata. It's a massively parallel machine. But the other alternative coming from the cloud is a scale out. You can have thousands of simple machines connected together in order to process a large amount of data. And that's, I would say, the cloud approach. So when talking about data processing, Jim Gray said there are three levels: data management, data analysis, and data communication. Data management means two things: data retrieval, data update. Data retrieval, we have the chance of having Code's theorem in order to demonstrate he defined an algebra which enable SQL to be a success, an implementation factor of Code's theorem. And then concerning update, anytime you're doing a transaction, you're applying Gray's theorem on transaction. You know that, but when you're doing a transaction, you reserve something on internet through your mobile or your PC, then exactly the same, you apply Gray's theorem on transaction update. So that's the two major contributors of data management. Concerning data analysis, what is the most promising area? Of course, we're talking about machine learning. Machine learning is a new name for statistics applied to big data, and deep learning. Deep learning, I would say, I discovered deep learning 10 years ago, but I'm an enthusiast about it because that's an engineering tool, a nice engineering tool in order to see everything as an image. And then data communication and internet. So I talk about Jim Gray, and Jim Gray state the fourth paradigm of science. The fourth paradigm of science means we enter the world of data science, the science of data. So he was dreaming of a world in which all the data management tools, data analysis tools, data communication tools will be free on the planet and will be used to improve human mankind. First paradigm of science, 1,000 years ago, it was experimental science. We duplicate and we replicate some physical phenomenon in order to understand them. Then 100 years ago, that was mathematics getting in, theoretical. And then some decades years ago, in 50 years ago, 70 years ago. That was computing coming around with simulation tools. And then finally, we entered this fourth paradigm of science. So we have to pay a tribute to him, because many projects we have today, which are open source for data management, are coming from the fact that Jim Gray, who received this Turing Award in 1993, pushed forward. So we enter in science this fourth paradigm. And big data, in science, it's a couple. And I say even that it's an art crossing different science. At many levels, you have to be creative. You have to be creative in order to decide what type of sharding, splitting you will use to analyze in parallel a large amount of data. That's an example. You have to be creative in order to define characteristics in deep learning. So you have many possibilities of being creative in terms of intersection between computer science and mathematics. So concerning data management, we have plenty of SQL tools. I quote some of them here. And we have an open source platform for parallel data processing, which is called Hadoop and MapReduce, which is coming free from Google and Yahoo. And MapReduce is very interesting. That comes from functional programming. 2 functions are enough in order to do any type of search within a huge database. And that's a typical example we're sharing with students, how we can do, for instance, a join with MapReduce, a join between 2 tables with MapReduce. Of course, we can do everything, so we can do that. So that's very interesting to be a query engine is built around 2 functions, map and reduce. And that's the Datum Google gave to the open source community in order to make it open to everybody. And then we have the data analysis. And here I put some other reference open source, like R language, Python, TensorFlow, Caffe, and others. Plethora of big data management system, plethora, huge amount. And here it's a picture from Haslet with 100 systems. And you see some classification, relational, new SQL, NoSQL, non-relational, analytic, operational, K-value. It's exactly what we did in order to structure this view. We built what we called data paradigms. Data paradigms, top-down approach and bottom-up approach. Top-down approach means from the real world, first we define the schema. And then after defining the schema, we can put in the tuples data. And that's a typical top-down approach with followed by SQL2, SQL3, ODMG, and Sparkle and the semantic web for structured data and semi-structured data. For unstructured data, it's a bottom-up approach. We're starting from the data. And data, there is no schema, no metadata. So any record could have its own format. So not only SQL, and kind of merging of these 2 major approaches called new SQL. So if we just would like to look at Garnet like proposed by Mike Stonebreaker concerning data and processing, the database market, and to see how the different standards SQL2, SQL3, and ODMG fit there, you can just look at this chart and you see the figure. Okay, the SQL2 and the major actor of SQL2 are moving towards SQL3, which represent today the standard of the present and the future. SQL3 integrates objects. And the way they integrate objects in SQL3 is through pointers. So pointers are integrated into the relational data model, which is a value paradigm. Everything is value in the relational data model in SQL2. But then with SQL3 and with objects, we introduce the pointer chasing. So different operator associated with pointers, referencing, dereferencing. We mix them up with SQL. And what is important is an object, the simplest definition of an object, it's a couple, OID and value. And if we look at no SQL system, we talk about K-value systems. K-value system mainly with value could be blob, binary large object, value could be a column or a set of columns for decision support, or value could be a document, a JSON document. So that are the three types of K-value systems we have within NoSQL. And we have also a bit apart the graph SQL system, the graph data model. So you see here the three major standards. And the future, definitely 99% of the market, of the data, structured data market is for SQL3. You may see the figures. So concerning structured and semi-structured data, we have value paradigm, pointer value paradigm, and predicate value paradigm with the web data. We have also concerning database contribution to computer science, some properties. Here is tips, meaning transactions with ACID properties are part of the database contribution to the world of computing. Then SQL, non-procedural interface. Then persistency and page memory coming from operating systems. That's part of any DBMS today. And finally, the strong structuration with a schema. That's a tips property characterizing structured data management. Same with objects, it's the RISE properties: reusability, inheritance or polymorphism, identification, complex, and encapsulation. So that's a RISE property characterizing objects which do not exist in a relational database system. Then semi-structured and unstructured data. I just noticed there is a storm close to me, so I hope everything will continue quietly, but there is a big storm around. So semi-structured and unstructured data, we're talking about what? Web data, data coming from the web for semi-structured data. Then Hadoop and MapReduce with a key contribution to any DBMS system, any database system in the market, which is Hive, which is driver, enabling any structured database system to access any NoSQL system. So Hadoop and Hive. Then analytics, that's the objective. The fantasy is real-time data analysis with machine learning and deep learning. And of course, there is always a time dimension, real-time data, and we may use tags, we may use timestamps in order to do that. So you see the different properties representing the different words, and using these properties, RISE, tips, and what, then we can classify all the different systems and we can present them. That's what we did in a conference on data paradigms, which is part of the graduate course. Just look at the Gartner's quadrant on DBMS. You will see here Oracle is leading the market with Microsoft, SAP, and IBM. And we have also other actors, key actors coming behind. But interesting also is the future of DBMS market in the cloud. And here we see new actors coming in like Amazon and Google. Amazon and Google are getting in. Oracle is still the leader, but Microsoft, Google, Amazon are stepping in. And that's part of the future. That's just an analysis of the database system of the future. So what means big data management after COD? AC, it's not after Christ, it's after COD. Ted Code was the most important contributor in data management system in history due to his theorem and its model. Just imagine a paper written down in 1968 on August the 19th, by the way, it's very precise, 20 pages. It became a market of $20 billion US 50 years later. That's tremendous for a theoretical paper. So TED Code. And that's the foundation of anything. That's the foundation of SQL. You cannot understand SQL without knowing codes relational data model. But after him, there were enrichment. And I notice here, for instance, Chris Date and Mike Stonebraker talking about object, putting pointers into the picture. Then Tim Berners-Lee with predicate value and the web data. Then Chang from Google, everything is k-value, pushing the NoSQL system. Then Stonebraker saying, whatever you're thinking about the future, it will be based upon SQL. SQL is capable of handling many enrichment. And then you will see the debate between everything is polystore or deep learning, everything is an image. And you will see the tribute I gave to Évariste Galois, everything is a group, in order to formalize every type of data today. So bottom-up approach, NoSQL, base property. There is an alternative theorem of the one given by Jim Gray, is the one given by Eric Brewer, professor in the same university at Berkeley, on unstructured data. And very simple is to say that's his theorem. You have three basic properties: consistency, availability, and partition tolerance. The network will have different partitions. Within that partition, student data could be updated, could be made available, etc., could coexist. And at a certain point, they should converge. And therefore, he said, on the three properties, you just can have two of them. That's CAP theorem. You can have either consistency and availability, availability and partition tolerance, consistency and partition tolerance. That's his theorem. And that's a pending of the Jim Gray's theorem about consistency and availability. So NoSQL means no schema, no metadata, no relational, no join, no data format, no ACID, just base property. So I'd already quoted that point concerning NoSQL system, 3 k-value systems with value being a blob, a JSON document, or a column. When it's a column for decision support, or graph-oriented. So that's the 4 families of NoSQL system. And looking at complex data, you will see ODMG and SQL3 are the traditional standard for complex data, and how NoSQL and NewSQL are fitting in the picture, in the chart, when we talk about ACID properties and transaction support. That means that's opened the door to NewSQL with VaultDB as a representative, for instance. So SQL is not a fixed standard, it's a strongly evolutive standard. A lot of major contributions, evolutions, and I will show you an example to different systems. I take my traditional example of pilot, plane, and flight. Pilot describing the pilot of the company, the planes of the company, and the different flights. So that's a typical relational database schema. SQL2 or codes relational algebra. I'm interested by the pilots from Nice driving a plane from Nice. So I need to do a join between the two table pilot and flight, select the output I want is pilot number and pilot name, and I give the equation and I give the qualification. Same in codes relational algebra, which is underlying SQL. The relational algebra is a demonstration that SQL is implementable. And we say the 2 major lessons from codes relational data model. Codes was a mathematician. He was capable of reduce the concept to kernel of concepts, which are teachable and implementable. Teachable and implementable. And that's a challenge today we're facing with big data. In SQL3, we introduce pointers. So here the pointers and the dereferencing operator is symbolized by a blue arrow. So it's a dereferencing operator. We introduce a new type of attributes which do not contain values but pointers, like line pointers called row ID. And here the same question is written this way in SQL3. In object query language, the pointers are bidirectional. So they enable to go from one class to another. They correspond to predefined joins. So you do a joins by following pointers in the from clause. So we started from pilot number and pilot name, which are in the class pilot, and we follow the pointer perform flight to go to another class, which is the flight, and we indicate here the qualification. Then we have a Sparkle. Sparkle, you are working on graphs in Sparkle. So where are the pilots from Nice driving a plane from Nice? In Sparkle, you have select where, and you see the identification. The question mark before the name means the result and means the graph you are interested to go into. So into the graph pilot, into the graph subgraph pilot, subgraph flight, what is my interest? Then I took two different NoSQL systems. Initially, every NoSQL system has its own proprietary interface. And except MongoDB, all the major NoSQL systems are moving towards SQL. They are changing their interface. So I indicated two of them, Nickel, and one QL is pronounced Nickel from Couchbase, and CQL for Cassandra. And look the way that really looks like SQL. Select for the same query, select PIL number, PIL name from pilot, where any flight satisfies departure city equal Nice and address equal Nice. And same with CQL3, you see it's a join each flight on, so we get the flavor of SQL. With graph query language, we introduce some new concepts. Name of the pilots who perform a flight from Nice with a Boeing 747. Here I have to go through a subgraph, and what is interesting here is that the from clause introduce a graph, not a table. So in GQL, which is yet to come pretty soon, in the next month, we'll have this extension of SQL called graph query language. We have some specifications which are not yet finalized, but I gave you the flavor here. So from graph means you working on graph, not on table. And you have the match clause. And the match clause is a clause of pointer chasing within the graph. So it's what I did here. Then you have the new data type coming in, like a JSON data type coming into SQL. In Postgres in 2013, Oracle 2013, 5 years ago in SQL Server from Microsoft. Every other DBMS has a JSON data type. So we can create a JSON view as, and you see in JSON the document is defined by a couple attribute value. So here we indicate what we're looking for. We create first of course we create the data type which contains a JSON document. I created pilot with within pilot the flight report, which is a JSON document, and then I can select all the reports from pilot, and I can create a JSON view of relational database system, etc. And we can play between JavaScript and relational representation. So we could sketch today, it's what we're doing in the course, what are the major functions expected in the future big data SQL coming soon. Coming soon could be 2 years, 4 years for business reasons, but it will come. And it will take some key functions we overview just now, like the fact having from in the from clause the external table. Within internal table, we have external table that exists today in every database engine. External table means a NoSQL database. Then we have from graph. We may have graph also. And in the where clause, we may have partition. We have the match clause for graph and the partition. The partition because when we're talking about Hadoop, we partition the data in order to do parallel processing. So we'll have this kind of functionality within SQL. And what is a major research existing today from a theoretical point of view is a way to build a unified theory for big data management. We saw 4 types of data variety when putting new SQL: structured data, semi-structured, unstructured, new SQL, and data science. And behind that, there are set theory for structured data, graph theory for semi-structured and unstructured data, matrices for new SQL and data analysis. So we have 3 different mathematical universe: graph, sets, and matrices. And what we need here is a uniform theory in order to address this. Of course, we also have specific extensions of SQL, like the one we just saw concerning hierarchical data like JSON, XML, graph data, and tabular data like OLAP. So here, to look at the mathematics, I will just quote it. There is a complete seminar on that and a complete module of the course on that. It's the category theory could provide this formal uniform framework for polystore management. And this stems from a genius in mathematics called Évariste Galois. He was killed when he was very young. He was he was 21 years old, and he was sure to be killed because he was well, I will not go into his story. Go into Google. It's fascinating. But he was a Republican in the era of monarchy. He was an anti-conformist. He was a Republican, and there was some provocation, and he was killed. He was faced with the police in a duel. No chance at all, like Pushkin, no chance at all to win. So he was killed. And the night before, he wrote down what is the basis of the category theory, the group theory. And you may say today in mathematics, I saw in my University of Nice, there were a course on Galois sets in bachelor. So in bachelor in mathematics today, and that's the night before he was killed, he spent his night writing down 15 pages, and he sent them to Auguste Chevalier. That was published in the Annals of Mathematics. And I was very pleased to see that people from MIT, when they work on associative arrays, which is one of the 2 major theory, they quote Évariste Galois as a key contribution to this theory. So just a tribute to this guy. So we're talking here about data refinery, structured data, semi-structured data, unstructured data. We talk about extended data types, matrices, graphs, JavaScript, object notation, objects, etc. We talk about data mining for structured data or machine learning and deep learning. That's a data refinery. And here we have these different sources, structured data, semi-structured data, and structured data, are converging towards what we called a data lake. And the data lake tries to give a uniform representation of data in order to make analysis straightforward. So machine learning and deep learning on top of that to infer capta, information, and knowledge insight. So here, that's a polystore approach. So we have a dual approach for data lake, either polystores or multimodal data stores. Both coexist, both approaches coexist. Polystores, we integrate different sources of data. Multimodal DBMS, we have one single integrated DBMS with different models. In whatever the case, we need a uniform framework. So polystore, we have an application. The user query working on this uniform framework is decomposed, and every data source, every data store manage the sub part of the query. In order to build this bridge between SQL, NoSQL, and new SQL, and these different sets, graphs, and matrices, and linear algebra, there were 2 major proposals. The category theory, we started by Microsoft Research in 2011, and recently, 4 years ago, Oracle Research with University of Helsinki proposed also to use category theory, which is a multi-directed graph approach, which has the quality of being teachable. And for mathematicians, there is another approach which is convincing, but for me, for computer scientists, not for computer scientists, for mathematicians, I would say, that's associative array from MIT. That's also 5 years ago. They work on the same. So we have two different approaches, and that's present research. We need to work there. Still looking for a couple of PhD students who would like to share with us, and the University of Helsinki works to be performed in that field. So data science is the second aspect. We talk about data management, and now I have to talk about data science a little bit. Data science was data scientist was declared in a Harvard Business Review the sexiest job of this millennium. So that's interesting. And interesting to see also the computer science evolution. IBM, for instance, 10 years ago decided not to talk about computer science anymore, to talk about service science. And now everybody's talking about data science, following the first paradigm of Jim Gray. So computing moves from computer science to service science to data science. And when talking about artificial intelligence, we need to talk about what is intelligence. And here that's a huge debate. It's you can write books on that. Very interesting book by a French guy, Yann LeCun. It should exist in English. Quand la machine apprend, when the machine learns. He got the Nobel Prize, which is called the Turing Award. Like he was, I think, the only French guy who got the Turing Award. I have to check, but I'm quite sure of that. After 3 of them I already quote in this webinar. Of course, Ted Codd received the Turing Award, the Nobel Prize, which didn't exist in computing, replaced by the Turing Award. So Ted Codd, then Jim Gray, of course, for the transaction theorem and many other things, and Mike Stonebraker for his contribution to database management systems. That the 3 database people who got the Turing Award. And concerning deep learning, artificial intelligence, we have to quote 2 years ago, in 2019, Yann LeCun with 2 other colleagues from England and the US and Canada, he got the Turing Award for his contribution to deep learning. And that's very interesting to read this book, to understand pretty well what means machine learning, deep learning, and how these ideas of convolutional networks are stemming in the head of researchers. We got somewhere an intuition. He got the intuition, and then he did the formalization. And that's interesting. And artificial intelligence, before going into the way, has the same age as computing. I look at history, and even when we talk about connectionism starts in 1943, like the Turing machine. So definitely people started looking at the way we could emulate the brain with the machine in the 40s. And the word artificial intelligence has been pronounced in 56 in Dartmouth College. And AI will contribute drastically on the economy of the future. Every job will be impacted. Every job, from health to transport, from finance to education, everything will be concerned. Even in your private life, to check your investment, etc., you will have an assistant in your pocket. So here, that's our figure given by Harvard Business Review, by Yann LeCun, and interesting by the Peter Narvik, the current Google head. We don't have better algorithm, we just have more data. And whatever the feeling today, and I read somewhere that if we look at intelligence of a rat today, it's 1, of human being is 10. If we look at AI today is 1.1, very close to the rat, okay? But it's highly specialized. And Jan LeCun talk about AI paradox, meaning no common sense. A machine can detect a cancer in your brain by analyzing IRM, of course, but this same machine cannot do a coffee for you, okay? So highly specialized and no common sense at all. Very impressive gaming milestones in artificial intelligence. I quote here Deep Blue beating Kasparov in the chess, AlphaGo in the Go, and recently Libretis won a poker marathon. Carnegie Mellon won 1 million and more and 70,000 US dollars, playing against three poker champion. So some concepts behind machine learning, deep learning, and artificial intelligence. And you see how one field is within the other. Artificial intelligence is not on the shelf. You don't have a product. You don't have one technology. You have, when talking, I talk sometimes about digital algorithms. So as soon as you're writing a computer program, you're doing some artificial intelligence. So artificial intelligence could be the word of computer science today. And the difference is here. For instance, in traditional in traditional programming, at the input you have rules, you have data, and then you get answers. That I will say the first level of artificial intelligence, first generation. Then we have machine learning and deep learning. With machine learning, we have labeled data and answers, and we get rules. With deep learning, we still have data. We have tokenization, transformation of any format into an image, for instance, to be analyzed, and answers. And we generate data as an output, and of course, we get some prediction. So both machine learning and deep learning are data-driven. I said initially that machine learning is applied statistics meeting big data. I had a professor in statistics. I remember this professor, he got a very interesting quote from George Box, said every model is false, but some could be useful. That's a sentence you may hear many times when talking with data scientists. And concerning machine learning, we may define a very simple equation, y equal f of xy. F is the real prediction function. We have two types of variable. Y is the target variable, xi is the predictive variable. And of course, f is the real function, prediction, and we try to have small f, which is close to the real one, the predictive one. And in order to do machine learning, we have three major models: supervised, unsupervised, and reinforced. We have also adversarial, putting some probability there. And supervised means y could be a value or a category, and we have families of regression and classification there. And then we have unsupervised with no y, and here we have clustering and association. That's a major. Of course, you have maybe 100 machine learning methods today, but that's the most important one you may feel comfortable with. Supervised means data labeling. And reinforcement is the fact you improving by trial and errors, etc. It's a typical learning paradigm. Artificial intelligence is born in '56, exactly in August of '56. The word was coined by two professors from MIT, Marvin Minsky and John McCarthy. And that has been followed by the Moon Project and If you go to that quote, you will be surprised to hear Sputnik. That was kind of answer. John Kennedy later wanted to fight and to push, so they said, give us some dream. So the moon dream, the moon project, what is called the moon project. And the moon project for John McCarthy was artificial intelligence. And there were two major winters between that time and now, until 2012 exactly. Until 2012, for instance, ARPA in the US, which is financially supporting 50% of the research in universities, decided to stop any funding of artificial intelligence. And there were some people who survived and people who demonstrate in 2012 that some aspects of artificial intelligence, namely deep learning, neural nets, and deep learnings, it's a rebranding name for neural nets. So neural nets could be very interesting in order to manage picture, video, sounds, etc. And then demonstrated. And there were two major reasons for that: big data and graphical processing unit, GPU, processing power. GPU enabled to do linear algebra, to do matrix multiplication. And matrix and linear algebra are the bedrock of machine learning. And we cannot talk about artificial intelligence without looking at what happens in the chips. The chip market, so not only the software people, the mathematicians are there, but in computer science, the hardware people, they are doing an impressive job. And so silicon for AI could be could be CPU, could be ASIC, but today you have to look at GPU, graphical processing unit. And here the idea is to perform matrix operators, linear algebra operators. And today, high-level programming languages are compiled to the GPU, like Python, Java, etc. And concerning smart chips for digital neural nets, the founder of NVIDIA, after the founder of Intel, Mr. Moore, demonstrated that Moore's laws is obsolete. Obsolete due to the parallelism you could have with NVIDIA and GPU chip. I give that that figure concerning NVIDIA of 2015, because 50% they born in the game industry. So they provide GPU for graphics processing. And they were, I would say, bright enough in order to understand that they could have a lot of revenue coming from other fields than the gaming industry, than the graphics. And at that time in 2000, so 5 years ago, more than 50% of their revenue comes from video games, but then from the car industry, for smart cars, when you see assisted driving in cars, self-driven cars, etc., they use a lot of GPU, a lot of processing. So we have here at the electronic level, we have here a jump of improvement with the GPU. And I like to quote a research project from Intel on neuromorphic computing, and I put here a picture of the cell of this chip. This chip contains 130,000 neurons, artificial neurons there in a chip, 100. And you can put thousands of chips of this type. So millions of neurons in order to work on digital neurons. So I would say the electronic industry will provide key contribution to this field of artificial intelligence and data analysis. I will not talk about chatbots. That's another word to see application of a robot and on the chats and in the social networks. Students in marketing around us are using that kind of chatbot in order to infer from the websites information of interest. And I would like to give some words on two types of AI, two types of intelligence. In order to illustrate symbolic AI versus connectionist AI, when you see GOFA is good old-fashioned artificial intelligence based on rule system, and connectionist AI is a new way to imagine based upon deep learning. Here, the way you learn a language. I remember a discussion I had with Alain Colmerauer. He's a colleague from the University of Marseille in the 80s. I became a full-time professor at Nice due to the fact that Alain Colmerauer was reporting on the fact that I was candidate there. So I had to meet, I had to talk, and we had a very interesting talk on Prolog. He was invented with his team at University of Marseille. At that time, he was sponsored mainly by military. It was the Cold War, so you could imagine that the automatic translation between Russian and French was of interest with Prolog. But it was interesting to look at the way Prolog was working. It was an AI tool based upon rules on the form of if, then, else. Okay, so we try to summarize expertise with a set of rules. When it's very narrow, it could fit. When it's not narrow, it could be surprising. So just look here at the proverb in French, L'esprit est fort, mais la chair est faible. The spirit is willing, but the flesh is weak. Very nice. I translate in front of him, we discuss and translate it into Russian. I'm not speaking Russian, so I said, okay, let's take it as an input to Prolog and put it back to French to see what our Russian people understand of this proverb. And the return, the intelligent return was vodka is strong, but the meat is soft. I'm not sure my colleagues from Russia will understand perfectly that sense. And here you have the major difference between symbolic AI based upon rules and connectionist AI. How a baby is learning a language by big data, by repeating. So it doesn't apply any rule. It doesn't know grammar. It doesn't know the grammar. Is not an expert in grammar, but he knows by repeating. He can use the future sense if needed, the past sense if needed, just by repeating. That's a connectionist approach based upon big data. And of course some part of intuition. And symbolic AI is just rule. So if you look at the proverb, for instance, the spirit is willing, but the flesh is weak. The system said, okay, flesh, what kind of synonym, what is a rule I can use in order to define a synonymous word? So instead of share, he was using meat. Okay, so meat is a good translation based upon rule. And then what is strong for a Russian eating when eating meat? Well, it could be vodka. So they say those vodka is strong, but the meat we don't say weak. We say in this case it's tough. So look at the rule system, intelligent rule system, good old AI fashion. Old fashion. So symbolic AI is based upon rules. That unwritten programs, many expert systems have been developed. That was a word which was used. There is a one called Mycin for infectious disease with more than 600 rules, which was not at all satisfactory. But Airbus is using it for landing an airplane, for controlling the landing of an airplane, very narrow area. So that's that has some concrete positive application anyway, even though it's today the first generation of AI, symbolic AI. Now we're talking about connectionist AI. And here is based on brain emulation, and intuition. Not rational, not formal reasoning applying rules, but intuition. Intuition is the heart, for me, of intelligence. And I put in green what is my definition of intuition. You will not find it on internet. It comes from discussion with a colleague, biologist in Africa. He talked to me one day about the sphex fly. Sphex fly is a special fly in Africa which can enter a deadly circle. At a certain time, he repeats routine. He repeats the same gesture until its death. It's a special. You can look at this strange fly called sphex. So what is intuition is the opposite. You don't do any routine. You get out the routine. You have a feeling. You got a feeling. You got something, and that's called antispexity. So here the idea is to emulate the brain. You will see that rapidly, and you will have a complete seminar from my colleague and friend Marco Gori on deep learning, and with Stefano Melacci, both working on machine learning and deep learning. So we just give you the concepts. So here they say, Jan LeCun said about the future, the challenge for the coming year is to make a compatible traditional programming, symbolic AI, and connectionist AI. The merging of the three worlds is promising for the future. That's a huge area of research. Biological neurons, brains, and computers. You cannot talk about digital neurons without looking at what happens in our brain. And that's interesting to get some idea of some figure there. That's a picture of digital neuron. You will see there are dendrites, inputs, and axons, outputs. Different dendrites and different different axons. We have more or less, some people talk about 85, others people are 90, I would say 100 billion neurons in our brains, and 20% in our cortex. 100 billion neurons. Each neuron has more or less 10,000 synapses. That means globally we have 1 peta synapses. Do not forget 1 peta is 10 to 15. So 1 peta synapses in the world. So that we may say that we have the capacity of memory for our brain is 1 petabyte. So beyond the 1 petabytes we will have problem. And each synapse can perform a computation 100 times per second, 100 times per second. So the theoretical synaptic computing capacity is 100 peta operation per second, 100 peta operation per second. Wow, it's not that bad, huh? So this power. So if we look at computers by the year 2050, we estimate computers could reach that level of power. And just look at the GPU card and just I didn't say also that in order to make that work, the power consumption of our brain is 25 watts. But if we look at GPU, 10 teraflops per second, but 250 watts, 10 times more, and just for 1 GPU, so 10 teraflops per second. So you will need 100,000 cards, GPU cards for brain to emulate brain computer power. So that's to give an idea of the power. So digital neuron follow the idea of different inputs and one output. And so we have a vector as an input. We have a vector of value, so x1, x2. We have different weights addressed to that value. Then we have a sum. We have a sum of all this input value, the weighted value. We have a sum, a sum function, and then we have typically we have a threshold. If the threshold is satisfied, then something is activated, otherwise no. So that's the basic functioning of a digital neuron. Vector of input and summary, and then we have a threshold to activate the output. So we may, and here we may say we have a formula, a very simple equation: the matrix A, the input vector X, and the output value B. So we have here this kind of linear algebra underlying theory. When we're talking about a large number of neurons, because here that's a digital neuron, and I said my colleague Alice Guyon from biology, it's a very simplified view, simplistic, of a natural neuron, but which could be useful when there is a very large number. That's interesting for philosophy. I know a colleague in philosophy is attending this conference, say that's very interesting to compare with the nomad of Leibniz, etc. So deep learning is rebranding of neural networks with more than 2 layers. Multi-layer neural net, hidden layers. So we have millions of neurons in hidden layers. So that's the idea. We have the input, we have the output, and in between we have hidden layers. And that idea, which brought to the Turing Award to Yann LeCun, Benjo, etc., in 2019, for convolutional neural nets. You see this word, convolutional neural nets. Convolutional means you have hidden layers. You have layers inside. That comes from a very simple idea. I think I quoted somewhere. Convolution, I will not comment that slide. Pipeline architecture, not either. Yeah, I would like to just comment this last slide on artificial intelligence. Is the fact that Yann LeCun explained in his book that when listening to 2 neurobiologists who got the Nobel Prize in biology, Hubel and Wiesel, talking about the vision of cats, they demonstrate in order to get the Nobel Award that cats have different layers of perception that explain the fastest answer they could give to any situation. And they say there are different layers of vision inside the cat brains. And I say, okay, let's build a neural net using that idea with the hidden layers of neural nets. So that was just to say a very simple idea. That's intuition. Comes from listening to people to another field in biology and taking care of that, integrating that into their field and capable of building them neural nets and use that ideas of hidden layers to extract characteristics, etc. I just check about time. I will not detail NFC, Li-Fi, blockchain. You will have a copy of the slides there. I will just make one comment there, saying about NFC, Li-Fi, and blockchain. That represent standards, NFC and Li-Fi, which exist today. NFC, the capability of extending the sense of a smartphone by touching. By touching, you can do a transaction. You can get an information. You can exchange data just by touching. And that's a world standard defined in Europe in 2004. And then you have Li-Fi, which is not yet a world standard. It's an IEEE standard, but using LEDs. LEDs integrate processors and oscillations generated by LEDs and their microprocessors enable to transmit data at a throughput which is 10 times more important than with Wi-Fi. So it's complementary, but it's high bandwidth internet through the light. So security advantage, so they don't go into the body, they can go into the electronic device through the walls. So Li-Fi will be definitely for indoors and maybe for outdoors tomorrow, for smart lighting, part of the future of everybody. So what kind of services we could imagine based upon this location-based information? You have to be under the light to get the data. So it's totally location-based. And then, of course, blockchain, which is part of a distributed, which is kind of a distributed secure database. And with blockchain, we invent an everlasting application, an application which will never stop. So you cannot say, stop it. No, it's there and it will continue. That's amazing. But we have 3 seminars on NFC, Li-Fi, and blockchain. And I invite you to follow that seminars. They are free on different websites. So I will go to NFC, to the first data. Somebody asked me once to give me equations for data. And I said the first data equation I found was E equal MC2. Data is an energetic resource, a raw resource. M is for multimedia. And computer alone doesn't exist anymore. It existed as a node of a network, computer and communication. And if we look at the future, data equation will evolve to MC3, still an energetic resource, a raw resource, ubiquitous systems, the smartphone in the pocket. The smartphone won the battle of the pocket. Everything which is on your bag or your pocket will end up into your smartphone. And then we have here the convergence of computer communication and consumer electronics. TV, cameras, etc. Li-Fi, I will not comment, I just quote it. We have beautiful applications in museum, blockchain. And let us decode as a conclusion the future. But here also, there are 3 dimensions of the future in the data economy. That's a caricature from a great guy when I was giving a conference in September concerning this, the data economy, the 3 dimensions of the data economy. I talk about smart places, the evolutions from tools to services to smart places, the bottom-up paradigm, and the fact that we enter a new world where the man is enriched with a computer in his pocket, which is more powerful than the computer John Kennedy had in the hands, or the computer which was used in the Apollo landing on the moon. So we have it on the pocket today. So it's called Homo ubiquitous, and we are all contributors, common actors to the commons with the data. So that's the 3 major dimensions I infer from 25 years of practice in proof of concepts we develop with students and industry, smart places, bottom-up paradigm, and Homo ubiquitous. So I will not talk about this, the danger, and we'll like just to finish with the spiralist innovation in a conclusion of the talk. In the data economy, everything is spiral. And this concept of spiralism comes from the guy who's close to me, and this guy is a candidate to be Nobel Prize of Literature. He's a wonderful French-speaking author named Franck Etienne. He's from Haiti. He's one of the most important intellectuals still living there. And he created the concept of spiralism. And I had an important breakfast with him to discuss whether spiralism existed also in science, not only in literature. And that's this conclusion I said, and I had the opportunity to work on Gary Pisano's quadrants on innovation, and I use this kinetics based on spiralism, as you will see. So innovation in data economy is spiralist. Innovation first is an invention meeting a usage. It's bottom-up and multidisciplinary, while research is top-down and tubular. So that's the definition, the simplest definition we may have about this concept of innovation. And talking about it, my colleague Gary Pisano from Harvard talked about 4 types of innovation in IT. Routine innovation. Every year you provide, for instance, a new smartphone, which is lighter with a bigger screen, better battery. That's called routine innovation, improvement of existing products or services. And then we have two disruptive innovations. Gary Pisano is working in economy, so we took that dimension, but we can take exactly the same in marketing, we can take exactly the same in many other disciplines, but here, the presentation today is just an economy. So we can have two disruptive innovations. Disruption in business model in economy, or disruption in technology, new technological concept around. And finally, the merging of these two leads to architecture innovation, a totally way to do with the things or services. You have the reference of Gary Pisano. So that's the four quadrants developed by Gary Pisano. You see, all technology, all business model is routine innovation. All technology, new business model is disruptive economics business model. I give an example of that. BlaBlaCar, etc. depends on that. Then we have a disruptive technological innovation, new technology, old business model. And that's the area where students are very active. For me, universities are engines of proof of concepts working with industry. And that's here where we spend every year many projects with master students working here on POC, proof of concepts, using disruptive technology, demonstrating the feasibility of creating new services using new ICT techniques. So disruptive technological innovation with the new technology and old business model. And then if you put at the same time new technology and new business model, you have disruptive architectural innovation like the cloud, like the App Store for smartphone application, and that's typically this. And what is interesting here is to put kinetics this way. So you see, we may start from economics to go and build a spiral, or you can start from a technical disruptive innovation. We talk from routine, then we build the proof of concept, then we eventually think about consequence for architecture in terms of delivery of the POC, of the proof of concepts. Then we identify clearly the new business data model, and then we go into routine again. So whatever the field in digital data innovation, I put here NFC, Li-Fi, blockchain, big data, deep learning, we are into that spiral. And some companies, Google, Oracle, Microsoft, Amazon, etc., go into different spirals inside their companies. So that's a very interesting and passionating area to demonstrate that working on innovation is working on a multidisciplinary with other colleagues from other disciplines to build a multidisciplinary vision. Conclusion. First one could be, I hesitated between this one with Sister Flora managing an orphan house for 30 years in Haiti. Our master is delocalized in Haiti, has been delocalized there for 20 years. So we had to meet this extraordinary person, and she said, an ant can be an elephant. An ant, let's just imagine with a smartphone, you can change the world. And the last sentence Karl Marx was supposed to pronounce was, if you cannot change the world, try to change your world. So that was kind of wisdom. But then conclusion two is inferred from a quote Frank Etienne Bott in his book, the Cao-Babel spiral, he gave it to me. He said, and that's a message for the students, be innovation various. Try to be innovative in your life, in your professional life, and build interesting stuff. So that's, and if you have any questions, do not hesitate to ask them. And I know there are some of them, but I leave Mishket eventually comment, and then I put here some information. Yeah, I said error humanum est. and you will see after that that Datum and West. Then I said, I had an interesting book I received. It was last summer, an article by Professor Valentin Venturin in August. I received that article, The World as a Neural Net. You see the world as a neural net. I think that was interesting. And you saw that how category theory, I just quoted, is I would say the promising framework, formal framework to handle any type of data management in the future for data lake construction. And then some quotes from John Gage, one of the founder of Java at Sun Microsystem. When he talked to our students, he said, if you are crazy, it's possible. Remain open to creativity and innovation.
Thank you, Professor. So
okay, so maybe some questions, you may quote them. I leave you, Mishket, yes, otherwise exactly. I have problem to read them.
Some questions. So the first question is, can you explain more the aspects of data mining correlated to big data?
Okay, the word data mining is used mainly for structured data. I talk about SQL, I talk about SQL2, I talk about the relational data model defined by code. That's a word of structured data. And when we use the word data mining, that refers to this structured data word. When we talk about machine learning and deep learning, we talk about any type of data. Could be structured, semi-structured, or unstructured, different sources of data. And then we do not talk about data warehouse used for data mining, but data lake used for machine learning and deep learning. So that's a major difference. The variety of data we're taking into account. Of course, within SQL, we have specific operators like OLAP operators in order to do the multidimensional data analysis, data mining, based mainly on OLAP. You have the cube operator defined by Jim Gray also. Other question?
Okay, thank you. Yeah, we have another question. Can you be more specific in tokenization for deep learning?
Wow. That's a very interesting question, a large question. I'll give you a concrete example. Last summer, I had a group of 2 bright students working, and they are coming from mathematics and economics, and they were working in analysis tweets, in analyzing tweets generated in March and April in the US concerning the COVID. So the idea in this project was to build a POC, analyzing tweets and comparing the tweet progressions in the US with the progression of the COVID in the US with real data obtained from the university there collecting data all over the planet, where you can have all the data of infected people, dead people, etc. So the official data and the tweets, and tweets generally precede the real data. So we can have kind of map of the evolution of COVID in the US. So we concentrate on the month of March or April in the US. And of course, the Americans use a lot of tweets, not only Mr. Trump, but many Americans use it. If you have some symptoms, then you send a tweet to a friend or to share it somewhere. And putting, I have a headache, I'm coughing, I have some I have a fever, I feel bad, etc. So if you have that information, we analyze them, we put them at correlated keywords, and this way we build an image of the progression of the COVID in the US we could compare with the real ones. So the data used was the tweets. The tweets are public. The tweets are in the Library of Congress in the US, they are there. And then we have tools, an API, in order to go there and take the tweets for a given period of time and analyze them. So now that's tweet, and we use deep learning. So how we can transform tweets, which are text, into something which could be an input of a deep learning tool. And that's transformation. Let's call it tokenization. So transformation of any type of data into an input which is acceptable for deep learning. To make it simple, any image, a vector of a matrix. That's a typical use case. Other question, Mishket?
Yeah, we have another question. So it is, what are the perspectives of artificial intelligence development in parallel of nanotechnology development?
Well, I tried to put some a couple of slides on the chip because I would prefer to talk about the chip. You know that we're talking about nanometers there. The chip I'm talking from Intel research, which is a new kind of neural nets, chips for neural nets. You have 100,000 digital neurons into a chip, 130,000. We're talking about nanometers. Nanometers is 1 EO9. So that means we are talking here about nanometers. We're talking about chips. We can put that chips into a car. We can put that chip into many things in order to detect image, etc. in real time. The objective is in real time. So for me, the progress of AI and the success of digital neural nets is due to two factors, big data and chips. So I will not talk about nanotechnology per se. I will talk about chips electronics. And chips electronics in the area of nanometers are impressive in order to do matrix calculation. Do matrix calculation in a chip. 130,000 digital nets, digital neurons into a chip. That's a new way of neural nets. That's not, for instance, they integrate unpredictable data, because you may have predictable data, but of course you may have something unpredictable. COVID was unpredictable, even though some people say one day it will happen, or like, okay, that it was not predictable 2 years ago. So that's a black swan, if you prefer. The black swan exists always. And here, this kind of neural net they're trying to build is to try to integrate unpredictability.
Thank you.
So for me, that's a very important area. We need the software people, we need the hardware people at the nanometer level. Okay. Of course, there are medicines, and then in nanobiology, you can put in the body, strolling around, destroying cells. That's part of research which are conducted even inside Google on health prevention. The future of medicine relies in the 3P, talking with colleagues in medicine. Personalization, prevention, and prediction. Customization, prediction, and prevention. And that's just algorithms on data.
Thank you, Professor. So we have another question from Clea. She says, I see EBR logo in all your slides. What is it?
EBR is a name of the Master of Science degree of Estia, which is online. And some slides are coming from my course, my introductory course on big data management. And I mix up some slides from this. That's part of a EBR graduate degree and BR master degree. So that's the reason. That's the online master degree. And by the way, we started 2 years ago with the MBDS, the other master degree from University of Nice, and we continue with EBR this year. It's starting on January the 4th, and we built that master degree with Oracle in order to have a practical tools in the cloud available to students. Same for face-to-face students, but also for online students. So we have the computing power of Oracle in order to have good practical sessions in for the master students who are online. Just to say also for EBR, we infer from EBR 7 gradeos. 7 gradeos. Gradeo is a new name. It's a new name for skills, micromasters, micro-credentials in Europe. And the 2 first gradeo will be also online in a concomitant way on January the 4th with EBR on big data and artificial intelligence. So we take 2 courses from the 2 graduate courses from the master. My course on distributed big data management and the course from University of Siena on machine learning and deep learning, along with 1 course on data science from Oracle, and the 3 represents a gradeo, micro-credentials. So that's for continuous education. And that will be concomitant and starting in January the 4th. And also this new learning subscription from Oracle, providing complementary courses to our online master degree, and the gradeos also start in January. So that's 3 different things starting in January, which will be online, available on Fun platform.
Thank you. So if some of the attendees have other questions, please do not hesitate to ask.
What is important is that it's the beginning of a series. I'm in charge of these seminars from a scientific point of view. Next week, you will have Alex Ryan, professor in Deusto, University of Bilbao, in charge of a big data master degree there, which is very successful for continuous education, and which has some specialties in big data applications in sports. So Alex, we talk about big data implications exactly in 1 week. And then you will have 3 other colleagues, one from Tahiti in January, Alban Gabillon, and my 2 colleagues from and friends from University of Siena, Marco Gori and Stefano Melacci in January and February, followed by 2 startups presenting use case of deep learning and machine learning in marketing and in industry with UP and Bedrock. So reach seminars, not only for our students, it's open like today on Teams. You just have to register. There were 900 people registered, so that's impressive. Due also to Fun and Oracle involvement. That's a way to expose our master degree, our graduates to industry people and to students which could be interested in getting into that degrees, or computer scientists getting into the skills they eventually miss when they were students.
Thank you. So I think we do not have other questions on the chat.
Okay, so let's see. Let's continue next week and see you soon. And I will wish you to everybody big data and AI future for improving the best of us and the best of humanity. Okay, so
thank you, everybody.
Bye bye. Take care.